All right, today we're going to look at scientific notation. I'm relatively confident you guys have all seen this before and that you're comfortable doing this. It's a great example of exponent laws regardless though, so we're going to get started. We'll first look at the definition and notation, and then how you do multiplying and dividing powers, which are really just the exponent laws applied here, and adding and subtracting. This is the formal definition of scientific notation. It's some number, which you see the magnitude of that number has to be equal to or greater than 1, but less than 10. So it's a single digit and then a decimal. Can be negative, that's fine. Times 10 to some power. And this big Z means integer. You'll become really comfortable with what all of those mean. And an integer is whole numbers, 1, 2, 3, 4, 5, etc., and 0 and the negatives. So standard notation is if you're writing out all these really, really big numbers or really small numbers, just with all the zeros you need to, whereas scientific notation will kind of condense it, especially if you don't need things to be very precise. So scientific notation in this case, we're going to take a look and see where we need to put the decimal point, which is a single digit here, and then how far we need to move it. So times 10 to the first, to the second, to the third, to the fourth, to the fifth, and to the sixth. So this will be 1.27 times 10 to the sixth. With small numbers that works as well, but we're moving it in the other way, so we're going to have a negative exponent. Remember what negative exponents do from the last presentation. This is where we'd put it for that A, and it has to go in the other direction, times 10 to the negative first, the negative second, negative third, negative fourth. So that's 3.2 times 10 to the negative fourth. No reason I'm using green here. We can also convert it in the other direction, so we have negative 4.1. Okay, I'm going to decide where I put the decimal in a second. And this to the fourth, I should get a pencil, means it's going to be a big number. 10 to the fourth is 10,000. But I want to move the decimal over. There's to the 1, to the 2, to the 3, to the fourth, and then put my comma as needed. So I saw 1 spot, 2 spots, 3 spots. I'm sorry for that dot. It shouldn't be there. My marker just happened to hit it. And we can go in the other direction as well. So this says move it to the left, then 2 more spaces. We want to go back the other way. So 1, 2, and we may need a placeholder. So 5, 2, 0, 1, and I need to move it. There's times 10 to the negative 1, times 10 to the negative 2. So I do need a placeholder and a 0 here. Okay, what's really important to remember, calculators are not good at using standard scientific notation. They may give you something like this. You cannot write it down like this or you will not get credit. So it's not accepted in IB exams. What this just means though, pretty simply, is this is 2.4 times 10 to the 8th. It's exponent notation, okay? That's what that is. You have to write it this way or write it out if it's a small enough number, and you can't write it like this. You do need to be able to understand the flow. Multiplying and dividing in scientific notation is quite easy because this is just all different ways of multiplying. So we can regroup it and change the order thanks to the associative and commutative and all those transitive properties. 3.2, you don't need to write out all these different things. That's 3.2 times 2. I'll write it this way to make it really clear. Times 10 to the 8th times 10 to the negative 5th. Okay, and remember, thanks to those exponent laws, if 2 factors have the same base, you can add and they're being multiplied, then you can add their exponents. So this is times 10, and 8 plus negative 5 is 3. And 3.2 times 2 is 6.4. Okay. What's worth knowing actually is if I had gone over, I don't have a great example right here, if this were then 64 all of a sudden because or let's say this was 5.2 times 2, then I'd have 10.4. That is no longer scientific notation, and I would need to make sure I move the decimal and add 1 here, okay? I can give you an example right here. Once I know I have enough room, I'll do this one and then see what will happen if we have something that's no longer in scientific notation. Same thing here. If you're multiplying 2 things with the same base, or dividing 2 things with the same base, you can subtract their exponents. So I can do 8.4 divided by 4.2, which is 2. And 10 to the 15th divided by 10 to the 12th is just 10 to the 3rd. So that's fine. If I give you one more problem to see what would happen, how about I just do that really simple one again? 5.2 times 10 to the 8th, and that times, we'll say times 3 times 10 to the 4th I could reorder these, and what I would see, well, 5.2 times 3 is going to be 15.6. And I have two things being multiplied with the same base, so I can add their exponents. But this is not scientific notation. So it's important now to be able to say, I actually need to move that decimal over. Okay, so that decimal being moved over one place, 1.56. And then I'm gonna have to put it up here because it's 1.56 times 10 is this. Let me write that out there. So this number is that. And I still have times 10 to the 12th. And I could think of the same thing as this is 1.56 times 10 to the 13th. So do make sure that your final answer is in scientific notation if it asks you to put it in scientific notation. Raising to a power is also a really simple one thanks to the exponent laws. You do need to make sure that you're raising everything in those parentheses to the power that it's asking you to and not just the nearest thing. This, for example, says raise everything in parentheses to the third. So that's 2 to the third times 10 to the fifth to the third. 2 to the third is 8, and 10 to the fifth to the third, remember now we multiply, is times 10 to the 15th. That is still in scientific notation. I don't need to rearrange anything. Same thing here, it works with any kind, even these rational exponents, which is the same as the cube root. That's 8 to the third, or the cube root of 8 times 10 to the 9th to the third. That's pretty simple. The cube root of 8 is 2, and 10 to the 9th to the third, we multiply those, is 10 to the third. Also in scientific notation, so I don't need to rearrange there either. What does become a little bit tricky is when you're adding and subtracting, because just like with fractions, with terms, we can only add and subtract like terms. And if these are 10 to the 8th and 10 to the 8th, then they are the same, and that's quite simple. So 7.42 times 10 to the 8th plus 3.1 times 10 to the 8th. I'm going to do one step just to show it. If I factor both of those out, the 10 to the 8th, I get 7.42 times 1, that's easy, plus 3.1 times 1, which is easy. And this is just going to be 10 to the 8th times 10.52. Okay. You'll notice that this is not going to be good because it's not in scientific notation. I'm going to continue the logical steps with equal signs, 10 to the 8th. And in here, this is making sure that I'm writing it again in scientific notation. That's 10.52 times 10 to the first times 10. Good. I forgot a 0. 0.52. Here we go. To the first. And then again, watching those exponent laws, I can do, I want to multiply this through to there. This is not the distributive property. This is a times. It's not the plus here. So we don't do it times each piece. This is just going to be 1.052 times 10 to the 9th. Okay. It does get quite a bit more challenging when you have these unlike terms because you can't just add the pieces together. The laws of the exponents don't apply in this particular case in the same nice way you'd hope. What we're going to have to do is convert one of these to the other. And it doesn't matter which. I like to work with bigger numbers rather than smaller numbers. So I'm going to say that this is okay, I'll make this times 10 to the third. I guess I can write it here. I'll use a different color though, just to make it clear where one stops and the next one begins. If I want to make this thing times 10 to the 3, because the other one is times 10 to the 3, 0.2 times 10 to the 3, then I'm going to need a 10 to the 2. There, now I have my 10 to the 5th. So 3.70 times 10 to the 2nd times 10 to the 3rd. There's my 10 to the 5th. And I'm going to have to say, well, this now is times 10 to the 2, 370 times 10 to the 3rd, minus 8.2 times 10 to the 3rd. I'm using the same logic as up there. This is going to be, take away 862, so 361.8 times 10 to the 3rd. This is, though, not in scientific notation again. I do need to move it back. Okay, so I had some big numbers. This is 3.618 times 10 squared. And so that will be times 10 to the 5th, to the same logic. And this last one, same deal. Can't add these things together. I'm going to have to think through what I have to do in order to make these equally sized, equal magnitudes. I'm again just using a different color to see it here. If I want to make this to the 3rd, then I'm going to need to do 2.43 times 10 to the 7th times 10 to the negative 4 plus 5 times 10 to the 3rd. Okay, because this is going to be 10 to the 3rd, and that's going to be, excuse me, I should have made this a 3 to the negative 3rd. There we go. How about I rewrite that so it's very clear? 2.43 times 10 to the negative 7 times 10 to the 3rd. That will then give me the 10 to the negative 4th. I'm just going to get rid of this because it's quite messy. Plus 5 times 10 to the 3rd. And we can rewrite this moving over 0.0 here, making sure we're moving it over enough. And then I need 6 zeros, and then the 243 times 10 to the 3rd plus 5 times 10 to the 3rd. So it's going to be 5 plus, and then I have all of these little pieces. I don't actually need the plus. I can do that in my head. We have 6 zeros. And the 243 times 10 to the 3rd. And that is the scientific notation of that, even though that's a silly number. It's still in between 1 and 0, or 1 and 10.